My name is Robert, and I'm a Google developer expert for machine learning and the Google Cloud Platform. And for today, I'll be talking about microcontrollers and programming them for TinyML. So TinyML is machine learning, but on deeply embedded systems. Okay, so what are microcontrollers next? Microcontrollers are computers, but they're not computers in the sense of what we're used to. So we're all here because we're used to programming computers, laptops, desktops, phones. I think we've done a good job with that over the last 5-6 years. There's nobody here who doesn't know what a computer is. But this thing that you see up here is a computer. It's a full-fledged computer, but it's what we call a microcontroller. And that's because it's different. If you're wondering where the monitor is, where the keyboard is, there's none. There's never going to be a monitor and a keyboard. This is all you get. In fact, these pins will go away when you're going into production. So it's application specific. It does only one thing, usually, when you roll it out. So you decide on what you want it to do when you program it, and then you forget about it, right? It gets its input not from a keyboard or a mouse, but from sensors, right? And what are sensors? Sensors are things that are within the environment, and they're taking data, right? It could be temperature sensors, humidity sensors. It could be a button, right? So think of sensors like if you're approaching a door and the door slides open, it's because there's a sensor there and there's a microcontroller that tells the door to open. And when you walk away, the door shuts because there's a sensor that detects that there's nobody there and it shuts it. That's it, right? So, but if you think about it, who here programs those sorts of things? There's nobody, right? So typically what we do is we go to China and we buy them, we come back here, we deploy them, and we go to sleep. So next slide. Okay, right. So why would you be interested in programming microcontrollers? Well, because they're in a lot of things. There are billions of them out there, actually. More microcontrollers than people, and than computers, than phones, everything, right? So billions of them. And somebody has to do it, right? It's either we do it here or we outsource it. For now, it's outsourced. So we just go to China. We buy our cameras from China. We buy our watches from China. And everything comes from China, right? So how is it built? It's either built to Chinese specification or it's built to US specification. For now, maybe it's fine, but further down the road, we need to be able to customize our own setup, okay? So microcontrollers are in everything. Anything that is smart has a microcontroller in it. Your fridges, your washing machines, your microwave, your door locks, cameras, speakers. Yeah, so if you have Google Home, you have Alexa, they all have microcontrollers in them. Doorbells. If you use Fire TV, Chromecast, or any other Chinese one, they're in there. Your wearables, watches, earphones, even smart rings, smart glasses, they all have microcontrollers in there, right? We have applications in healthcare and in industrial automation, farms, you name it, they're all there. Right, next slide, John. Okay, so next question is, what does it take to program a microcontroller? And that's the key question. Typically, you need to know some, what we would call low-level language, C or C++. But nowadays, more microcontrollers are being released that support additional languages. So now there are some microcontrollers like the one we have up here that supports MicroPython. Some support Java for embedded devices. Some support even JavaScript. So there's an Esprino for microcontrollers. So there are a few language options that are coming up. No, not yet. You also need to understand electronic circuits because, recall your camera or your watch, it's not just the microcontroller that it has. It has a screen, or in the case of the camera, it has a lens in it. So you need to connect these things. You need to understand the electronics that goes into all of these communications. And then even more than the web and Stack Overflow, you need to be able to read documentation and the specifications. So interestingly, these things behave differently from our computers and our phones. So nowadays, you know, every mouse is standard, every keyboard is standard, every text field, is a standard input, date field, all those things. You don't have that here. Instead, what you have are general purpose I/O pins that you have to program as either input or output, right? So you have to read the documentation for every single one of them. Finally, you need to have a love of making things because, even with the regular programming, things break. You have to spend time debugging stuff. It's not easier here, so you need to love to make things. And there are a few things, at least, I'm sure a lot of people have heard of Arduino, even if you haven't heard of the others. Arduino and Raspberry Pi should be pretty familiar, but there are others that let you prototype as well. So Microbit, which is aimed at secondary school students, SparkFun, who are our sponsors for today, and Sony, they have some development boards that you're able to work with. Okay, so let's look at an example board pinout diagram. So recall when I said you need to be able to read the documentation. So this is one example of a board, and this is what the documentation looks like. It's not complicated, really. You have numbers from 1 to 20 at the bottom, 21, all the way up to 40. Really, what it's saying is that there are 40 pins on this microcontroller that you can program. The pins, depending on if you can see the colors, different colors have different meanings, right? This particular one is general purpose input and output. What it means is any green pin can be used for either input or output, general purpose. Black is ground or earth, right? So it's like you've got your power, so you can see power out here, and you've got your power in, where you'll connect your battery, your ground, because anything that is an electronic circuit must have power in and power out, right? The rest of it is color-coded, but that's what your microcontroller looks like. And so when you code it, you're going to be saying, as opposed to like web, where you're doing input and output of text or images, here you're doing input and output of voltages. Next slide. Okay, so for the workshop that we want to do, we're going to be doing something called wake word detection. Next slide, John. And what wake word detection is, so while I'm still talking, you can bring out your cameras, scan this, and you should be able to take a quick pre-workshop survey. What that will let us do, part of it is get information, and we also have a post. But part of it is we're going to run a raffle, and we have some microcontrollers that we want to give out because we're hoping that people will try their hands on something. So just do that, and we'll have your info, and we will run a survey. So the wake word detection that we wanted to demonstrate is what happens when you do when you say Alexa or when you say hello Google. So those devices usually aren't powered on. They are in sleep mode because they have to conserve power. And then when you say those very specific words, the microcontroller in there wakes up, and then it powers on the device, and then the device is ready to communicate with you. So if you think about it, if you've ever used like, an Alexa, when you say Alexa, the light comes on, and then it makes a sound, and then it tells you that it's ready to listen to you, right? So that's when it wakes up. So that thing that wakes up the device, that's wake word detection, right? So that's what we're going to be doing. Okay, yeah, so we're going to be giving out a very specific microcontroller from SparkFun Electronics. They were kind enough to send us a few. And I should mention that it's a huge favor, because if you've had any difficulty buying an Xbox over the last 1 year, it's because there's a shortage of chips in the world. but they were able to go and get us these things. So the same problem that Sony and Microsoft have, and all the car manufacturers, is the same problem that every other person has. But we got a few from them, and we're hoping we can get some more next year. So yeah, do fill in the survey, and even if we don't get you some this year, we'll get you some next year. Next slide. So for context, right, the TinyML workshop that we're going to be running is going to be three things. Electronics, because microcontrollers are electronics. Programming, because you're going to be writing code. And machine learning, because something as simple as, speech still requires machine learning, because you can't go around the whole world and record everybody saying something. So you need a way of having the computer detect whether or not the specific word that you're interested in was mentioned, right? So that's the whole task. Next slide. Okay, so to program wake word detection, there are a bunch of steps. I split it into two because the two sets of operations happen in two different places using two different languages. So on the left side is a machine learning task, which happens in Python. And then on the right side is a device programming task, which happens in C or C++, depending on your microcontroller. So the machine learning task, I'm sure that at this point in time, machine learning is familiar to a lot of people. You're going to have to collect data. You're going to have to train an NLP model, and then you're going to have to shrink the model to fit on the MCU. Now, I must have forgotten to mention at the beginning that the microcontrollers are really constrained, right? They come with, as opposed to your laptop, where you're talking 1.2 gigahertz up to 2.4 gigahertz. These things start with 64 kilohertz. That's the CPU, and then they get to megahertz. I think at best you can get like 170 megahertz or so, but that's high-end microcontrollers. So limited storage, limited processing power, but they have their benefits. They don't consume a lot of power, in fact, very negligible power. And for that reason, and again, they do not have operating systems. So you're used to your phones having Android or iOS, that's an OS. You're used to your computers having Linux or Windows. These microcontrollers do not have an operating system. So you're going to be programming bare bones. So when you're done with your model, you have to write an embedded program. So it's called an embedded program. And then you have to transfer your model into the program and implement a pipeline for streaming sound from the device microphone into the model, right? And then, of course, your embedded program is set to do something. And then when you're done, you have to compile. And this, of course, doesn't happen on the microcontroller. It's still on the computer, but it's just that this part is Python, this part is C. Compile and then flash. So you flash your program onto your microcontroller. Next, John. Okay. All right, so, wait. So we're supposed to do workshop, right? Okay. Okay, so we will jump into the workshop. Now, what we want to do here is you have to set up a tool chain for programming the microcontrollers, and that's a bit of a headache. So John is going to come up and do a demonstration of how to set up a tool chain. That microcontroller that we're using, right? Quick gist, hopefully 2-3 minutes. When you work with a computer, it has a processor, right? So a lot of us are used to Intel processors. So if you have a laptop, typically the question that people will ask is it Intel or is it AMD, right? So I'm sure we're used to that. When you come to microcontrollers, they have a different set of processors on them. And all of the processors that support TinyML, which is what we're demonstrating, those processors are designed by a company called ARM. And so ARM has also released something on AWS called ARM Virtual Hardware. So if you don't have a physical microcontroller, it's not an excuse to not get started. You can still get started. So just go to AWS and search for ARM Virtual Hardware, right? When you have your slides at the end, you will also find a link to all of these things that we're talking about. So John, over to you.
Right. So there is this set of instructions here that you have to follow. We have a blog post that we're going to show you. So we'll put up this link later. The first thing you do is to, of course, we have the board, which we have, and then have a terminal on the device you want to use. Depending on your operating system, yeah, and then plug a serial cable, onto the board, like I have done on mine. All right, so next we open our terminal. Depending on the operating system you use, you would use something different. And in that terminal, we get this program, which is part of what is used on the toolchain to do the compilation. From this link, you could get it for Windows, or you could get it for your operating system. And then you need to have Python 3. It's important that you have Python 3 because Python 2 has issues, which they have indicated here on your machine. Yeah. All right. And then we get to the toolchain setup, which is where we download, which is where we're going to use the software development kit. This Anbic Apollo 3 SDK. So all right, first and foremost, we get this GNU RM, and install it. And when we install it properly, by the time you run this, this particular command on your bash, it's not going to bring up any error. And then this is like the biggest part, essentially because of the data it consumes, getting the SDK. You download the SDK from this address. And then you take note of the SDK root directory. And take care of all these house rules. And then you are ready to load your applications. First and foremost, you check what port your device is on. And you can use this command on bash. Okay. Okay. All right, so like it was on the instruction, we use ls/dev/cu star, or if you are on Ubuntu or any other bash, or you use tty if you are on Mac. Yeah. It also works on Mac, by the way. Yeah. Okay, so this gives me a list of all the ports on my computer, and this particular one is where the microcontroller is currently connected. So I note that port name because that's what we've been told to do. Note the port name because you're going to use it to load the applications. All right, so there are some examples. The one that we want to show here is the second one, which is the one that uses TensorFlow microspeech. Yeah. Um, so we go into this directory up onto GCC, which is what we're doing here. Yeah, this is where we are. Bots, SFE, Edge, examples, TensorFlow, microspeech. Can you guys, the guys at the back, can you see the bottom of the screen? No, okay. I think I should do something like this. Yeah, kind of bring it. Okay, is this better? Yeah, all right. Um, all right, the next thing to do is to go with the make clean. We already did that, but it doesn't hurt to do it again, to clean the environment, and then, so then we type this command to load the, to do the compilation on using a specific baud rate. This is the rate at which the data is being transferred onto the microcontroller itself. For our own microcontroller, we're not going to use 921600. Yeah. We're going to use 115200 because that's the rate in which our board supports. When I say board, I'm still talking about this small guy. All right, so we do the compilation, and it didn't see my port. Yeah, so let me remove it and plug it back. Yes, I did select the right one. 1420. Was it? USB serial. Oh, 1410. Yeah, so I missed the port number there. Still not found. Ooh. Okay. Let me try to detect what the port currently is. Okay. Which one wasn't there? USB serial 1410. WC. Okay, so we finally got our port number. Yeah. So it does the compilation and upload failed. Oh, we didn't run make. Is that? Oh, okay. I I'm thinking with this guy. Yeah. Um. Yeah, I did. I think I got something, but it's not loading because I think it's talking to something else.
Is it WCH user there? Go and do ls, let's see. So I remember that there are two outputs. USB serial,
Yeah.
WCH, USB serial.
Yeah.
Use the WCH. You try
That's
this.
yeah.
If
That's
it
what I
doesn't
did.
work, use this, the USB serial.
That one doesn't.
It's moving, is it?
Yeah. It's not sending.
Hmm? Is it working?
No. It's saying report. It's saying it, but it's not sending it. Yeah. So
So here's why. It has rebooted. So you need to flash, you need to get into flash mode again. Boot
all right.
select.
Okay. So one thing we need to note is that this particular point, this, if you have code that is already running on the board, you will need to reset the board before you flash another code on top of it. If you don't do that, it's not going to work. Yeah. So even though this came after, but this instruction comes after with the assumption that your board is empty. But I already have things on my board. So I need to do this before I do this. So there is the 14 button you hold down,
You need your key.
and then you press reset and release, and then release the 14. Yeah, I repeated. Oh yeah, so now it's going through. Okay, so the link we're going to send to the blog post covers this situation where it doesn't upload even after reset. So what I did differently was to hold down the 14 key, the 14 button, number 14. Remember the pinout diagram, number 14 button here, and then press enter to do the upload. So upload is complete. We can now actually check to see if what we have done has worked. And I've turned it on right now, and you can see the flashing light. That means it's ready to hear sounds. We can open another terminal to see how it is responding to those sounds. Um, Let me get that port number again. That's WCH. Okay. Okay. So we can say yes. It means it didn't detect it. Or we can say yes, no, no, yes, no, yes, yes. Yeah, sometimes it acts like that. Yeah, so depending on how the voice interactions that we have used before, um, yes, no. Looks like he finds it hard to hear my no. No. He still didn't know it.
It's fine.
Yeah.
So I think let me say something.
Yeah.
Yeah, so one more thing here is that the system isn't perfect. Um, Basically, there's a whole lot. So remember the machine learning? Yeah. So just ignore the. So there's a whole lot to machine learning, right? We didn't go into that, but you need your training data, which is one of the things that we mentioned. Now, if you get training data from China, it's going to expect you to sound like the Chinese, meaning that if you talk here, nobody's going to understand what you're saying. So it's all part of the process. There's no knowledge that is wasted, right? So whatever knowledge you've acquired over the past 5 years, you're going to have to bring it to programming these things, right? So open your boxes carefully. There's a really tiny camera inside as well. So your board, you're having a box with 3 components inside that will let you do different types of experiments. So you'll have voice experiments, computer vision experiments, as well as accelerometer experiments.
So like you said, it's a raffle draw. We're going to spin, and if you're lucky, you get a Spark phone board, equivalent to what I used to do the raffle. I used to demo, and there is also, like you mentioned, a camera module that you can use too. All right, so are we ready to get the first person? Yeah, so we're going to. It's just 15 out of all of us that are going to be the luckiest ones. Let's go. This is my hands, though. Before somebody thinks I am controlling something. Hey, who is wisdom? Uzoma. Nice.
Just come over.
Yeah.
Yeah, camera. No, use yours. Yeah, so, you're already growing with Google. Congratulations.
All right, nice. Let's take him out. All right, let's get the next person. Aziz.
Is Aziz here?
Is Aziz here?
He has left.
Okay. Um, Nudoiba. Who's that? Ah, nice.
Okay, happy programming.
Brian. Hey, why is it people from that part of the room? What happened?
Congratulations. Yeah, just keep going.
Yeah, yeah. Ibukun Oladipo. Congratulations. Ayela Bukola. Congratulations.
Finally,
Yeah.
the other side.
Dusule. Ah, congratulations. Annabelle Lilo. Nice. Hey, well done.
Yeah, you look like a hard work programmer.
All right, Bankole. Did you script something to influence this thing? Bankole scripted. Congratulations. Oh yeah, oh yeah, oh yeah, oh yeah. Congrats. Okay, I think we're question. Yeah. Eniola, congratulations. Bello. Okolo Arthur. Okolo Arthur. Not here. Okay. All right. We've got Oyempemia. Right. So we have three more spins. Uh, is that Engetesia? Yeah, okay. The last two, let's see who will be lucky. Adegoke, yes. Femi, and the very last lucky person. That's a yeah. Congratulations, people. Yeah.
So, post survey.
Yeah. Yeah, so we have, just like you filled the pre-workshop survey, please go to this link and fill up the post-survey form. Thank you very much from Spark for Electronics.